Hello everyone, welcome back to my YouTube channel. I am Snehaaigali, pursuing my bachelor's degree at Sri Venkateshwar College of Engineering, Bangalore. My USN is 1VE22CS154. Today I am up with one of the most interesting subjects, mathematics. In that, I'll be representing this very interesting topic called vector space and linear transformations. First, let us begin with the introduction to vector space and linear transformations. Vector space are the mathematical structures that consist of vectors and operations such as addition and scalar multiplication. Linear transformations are the functions that preserve the vector space structures, maintaining operations of addition and scalar multiplication. Vector spaces and linear transformations are fundamental concepts in linear algebra. Now, next up is we have the properties of vector spaces. Those include a vector space must satisfy several properties, including the closure under addition and scalar multiplication. The next property is addition in a vector space is commutative and associative. Next, scalar multiplication satisfy properties such as distributive over addition. Here we have examples of scalar spaces. Now next we have example of vector spaces. It includes examples of vector spaces include the set of all real numbers, the set of all n-dimensional vectors, and the set of polynomials of degree n or less. The subspaces of a vector space are subsets that retain the vector space properties. Now the last one is the span of a set of vectors in a vector space is the set of all possible linear combinations of those vectors. Now, next up we have bases and dimensions of vector spaces. A basis of a vector space is a set of linear independent vectors that span the entire vector space. The dimension of a vector space is the number of vectors in its basis. Any vector in the vector space can be expressed as a unique linear combination of the basis vector. Now next we have another topic, that is linear transformations. Linear transformations are the functions that preserve vector space structures. They satisfy two properties, namely preservation of addition and scalar multiplication. Linear transformations can be represented by matrices. Matrix of linear transformation. Here we have an example, that is T is to U belongs to V. T of U is equal to AU, where U belongs to, that is small u belongs to capital U. Now next up we have the examples of linear transformations. Examples of linear transformations include rotations, reflections, and scaling. Matrix multiplication can be used to represent linear transformations. Linear transformations can map vectors from one vector space to another. Here we have some of the examples for that in the image. Now next is composition of linear transformations. The composition of two linear transformations is also a linear transformation. That is, mixture of two linear transformation can also be a linear transformation. The composition is associative, meaning is that the order of composition doesn't matter. The identity transformation is a special linear transformation that leaves the vectors unchanged. The composition of transformations, when the transformations being composed are of different types, like a translation followed by a reflection, then the order of the transformation is usually important. Now next we have kernel and image of a linear transformation. The kernel of a linear transformation is the set of vectors that map to the zero vector. The image of a linear transformation is the set of all vectors that can be obtained by applying the transformation to some vector in the domain. Here, third bullet. Now next we have is inverse of a linear transformation. An inverse of a linear transformation exists if and only if the transformation is bijective. That is, inverse only exists when transformation is bijective. The inverse of a linear transformation undoes the effect of the original transformation. The composition of a linear transformation and its inverse is the identity transformation. Here we have an example for that. That is, a camera is attached to a gripper robot arm. The camera can focus on an object to determine the frame relative to the camera. Find its transformation matrix for the object relative to the robot arm using the matrix below. Now you can get to know this topic better by going through this example. Now next up we have is matrix representation of linear transformation. How to represent linear transformation in the matrix. Matrix representation of linear transformations can be found by applying the transformation to the standard basis vector. The columns of the matrix representation are the images of standard basis vector. Matrix multiplication can be used to apply the linear transformation to a vector. Now next, let us see the change of basis. Changing the basis of a vector space involves expressing vectors in terms of a new set of basis vectors. The change of basis matrix transforms the coordinates of a vector from the old basis to the new ones. Linear transformations can have different matrix representation with respect to different bases. Now, if you go through this image, you can understand the change of basis more easily. The next up we have is eigenvalues and eigenvectors. Eigenvalues and eigenvectors are important concepts in linear transformation. An eigenvector is a non-zero vector that remains in the same direction after applying the linear transformation. The eigenvalue corresponds to the scalar by which eigenvector is scaled. Here we have an example. The eigenvector of the matrix are vectors that satisfy Ax is equal to lambda x, or it can be even represented as A minus lambda 1 of x is equal to 0. So, lambda is an eigenvalue if determinant of A minus lambda 1 is equal to 0. For that, you have an example below. Now, the next topic is diagonalization. Diagonalization is the process of finding a diagonal matrix that represent a linear transformation. Now, what is diagonal matrix? A diagonal matrix is a square matrix wherein all its non-diagonal elements are 0. For example, you can take a matrix as A matrix. You even have an example that is a matrix having elements as 3, 0, 0, and 4. Now next, diagonalizable linear transformations have a basis of eigenvectors. Diagonalization simplifies computations involving repeated applications of the linear transformations. Now next is orthogonal transformations. Orthogonal transformations preserve lengths and angles. Examples of orthogonalization transformations include rotation and reflection. Orthogonal matrices represent orthogonal transformation. Some of the transformations are, we have some of the transformations over here, which are first is rotation, next is reflection, and the last is translation. Now next up, the applications of linear transformations. Where all are the linear transformations used? Linear transformations have numerous applications in various fields, including computer graphics, data analysis, and physics. They are used for image processing, dimension reduction, and solving systems of linear equations. Eigenvalues and eigenvectors are used in many algorithms such as principal component analysis. Now, let us finish this session through the conclusion. That is, vector spaces and linear transformations are fundamental concepts in linear algebra. They provide a framework for studying and manipulating vectors and their transformations. Understanding vector spaces and linear transformations is essential for many applications in mathematics and another disciplines. Well, that was all about this session. Thank you so much for watching.